Today we're going to talk about the rational root test, or the rational root theorem. The rational root theorem says that if r is a root of this polynomial, then it can be written as plus or minus p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So if you're curious about why this statement is true, it's because in order for it to be a root, we need something like qx minus p to be a factor of the polynomial. So if this were a factor of the polynomial, we would set it equal to 0 and say that x equals p over q. Or x, if we change this to plus, then it would be x equals negative p over q. Why does this have anything to do with being a factor of the constant and q being a factor of a of n? Well, when we multiply this times a bunch of other polynomials, the leading term will have all of the x terms multiplied together. So it'll be q of x times all of the other leading coefficients. And a, 0, will be the constant times all of the other constants. So that's why it could be equal to a0, or this could be equal to an, but it has to be a factor for sure. And this is only for finding rational zeros. We can't find irrational zeros with this. So let's find all possible rational zeros of this function. So we can write out the values of p. The values of p are 10, 5, 2, and 1. And the values of q are 2 and 1. So what we know is that it has to be plus or minus one of these divided by one of those. So we could just divide by 1, so that would be plus or minus 10, plus or minus 5, plus or minus 2, plus or minus 1. And that's if we divided by 1. If we divided each of these by 2, 10 divided by 2 is still already listed. 5 divided by 2 is not already listed. 2 divided by 2 is listed. 1 divided by 2 is not. So technically we could write out 10 over 2, 5 over 2, 2 over 2, 1 over 2, but some of those are repeats, specifically 5 and 1 are repeats. So these are the 12 different roots: plus or minus 10, plus or minus 5, plus or minus 2, plus or minus 1, plus or minus 5 halves, plus or minus 1 half. So those are all the possible rational zeros. Now it's worth noting, because this is a degree 3 polynomial, you know that there can be at most 3 zeros, and they don't even all have to be rational. But these are the possible ones. Thank you. Find all zeros of this. So let's find the rational zeros first. So we have plus or minus 5, plus or minus 1, plus or minus 5/7, and plus or minus 1/7. So those are the possible rational zeros, but I didn't ask for the possible ones. I asked for all of the zeros. So I need to figure out which of these actually are zeros. And hopefully they won't all be rational. Anyway, let's try one, and we'll learn methods of being able to figure out which ones are better to try. But I'm gonna just try 1. I'm gonna see whether 1 is a 0 of this. So 7 times 1, this becomes 43. This becomes 43. 41. 1 times 41 is 41. Becomes 5. Oh hey, this one did work. So we know that one of the zeros is 1. That's one of my zeros. Now, we still have this list. All of these are positive numbers, so I don't really want to try something. Positive. I feel like if I put a positive number in, then it's going to not work, because it'll just make the numbers bigger and bigger. So let me plug in, say, something like -1. See if -1 works. So 7 times -1 is, I'm sorry, we just bring down the 7. -1 times 7 is, oh, this is going to be annoying. This is 36. -1 times this is -36. That's 5. -1 times 5 is -5. Ooh, this worked out nicely. So now we have -1 is one of the roots. Now we have 7x squared plus 36x plus 5 is what we're left with. So we have x minus 1 is a polynomial, x plus 1 is a factor, and then we're left with this. Things that multiply to 35 and add to 36. Well, 1 and 35 work. So now that we've gotten it down to a quadratic polynomial, we can say that we can use old methods, use methods that we're used to. So we factor by grouping, and we get 7x plus 1 times x plus 5. Or we could have done quadratic formula if we wanted, or completing the square. But now we have our zeros. So we had 1 up here. So x equals 1 was a 0. X equals -1 is a 0. Based on this term, 7x plus 1, that tells me that -1/7 is a 0. And this tells me that -5 is a 0. Sometimes we won't get as lucky, and if we say tried +5 first, we would get a number here. If this didn't turn out to be 0, we'd have to say, nope, that's not a 0, and then go back and do synthetic division with the original polynomial again until we found something that worked. There are methods of choosing more carefully between these zeros, these potential zeros, but that is how we can use the rational root theorem to help guide our decisions about trying what rational roots there could be. Thanks.